In this presentation, I would like to discuss the solution of an open loop optimal control problem using transcription and the interior point method. Historically, these problems have been handled through the use of calculus of variations. Due to the advent of newer computational capabilities, we will take a different approach. We will focus on a simple problem. Here we have a simple set of dynamics, x double dot is equal to a of t, where a of t is the control input, x is the state of the system. The boundary conditions for this system are at time t is equal to 0, where t runs between 0 and 1 second, x of 0 is equal to 0, and x of 1 is equal to 0. Also, there are velocity boundary conditions. X dot at 0 is equal to 1, and x dot at 1 is equal to minus 1. We also have an inequality constraint, and that inequality constraint states that x of t can never be greater than L. We would like to solve this problem, that is, find the optimal x of t and a of t such that the control energy is minimized. Our performance metric for the minimization of control energy is the integral from 0 to 1 of a squared dt. The first computational method that we use in order to solve this problem is transcription. Transcription turns a calculus of variation problem into a parameter optimization problem. In a calculus of variations problem, you're solving for a continuous time solution. In a parameter optimization problem formulated through transcription, you're solving for parameters at discrete times. So we would solve for the state and the control input at t is equal to 0, t is equal to big T, 2t, 3t, all the way out to nt. We now return to the original problem statement. In the original problem statement, we had dynamics. The dynamics were x double dot is equal to a of t. Using transcription, we can approximate the x double dot by a central difference approximation. This gives us a set of equations, a total set of n minus 1 equations that represent the dynamics of the system. In the problem statement, there were also boundary conditions. For the boundary condition, x of 0 is equal to x of 1 is equal to 0, we can write this in terms of our parameters. X of 0 is equal to x at n, which is equal to 0. For the velocity boundary conditions, we can come up with a similar equation. There were also constraint equations for the interior point method. These equations can also be written discretely. There are n minus 1 of these constraint equations, which include the slack variables. There are still inequality constraints. However, these inequality constraints are simplified using only the slack variable. There are n minus 1 of these constraints. So we would like to find a x and an a which minimizes this performance metric, where this performance metric is the integral from 0 to 1 of a squared dt. That is a minimization of the control energy. Remember, by using transcription, we're dealing with discrete variables. That integral can be approximated as shown here. we would like to perform this minimization with respect to the dynamics of the system, as well as to a number of constraint and inequality constraint conditions. First, the dynamics. The dynamics were represented by a set of difference equations, which can be solved for 0. And each of these can be multiplied by a Lagrange multiplier, and then they can be added to this representation of the IP. So this set of terms is associated with the dynamics. Likewise, we can take a similar approach for the boundary conditions. We can solve those for 0 and multiply by Lagrange multipliers and add those terms to the rest of this equation. We also had equality conditions for the slack variables. We can solve those for 0, multiply by a different set of Lagrange multipliers, and add those to the rest of the terms. And then lastly, we need to add this set of terms. These terms turn the hard inequality constraint for the slack variables into a soft constraint, a soft inequality constraint. So what are our unknowns? We have n-1 control inputs, n-1 state responses. We have n-1 Lagrange multipliers associated with states, 2 Lagrange multipliers that are associated with boundary conditions. We have n-1 Lagrange multipliers that are associated with the interior point method, and we have n-1 S's associated with the interior point method. The optimal solution is not found by driving the IP to 0, but by driving the gradient of the IP to 0. The gradient of the IP is found by taking the partial of the IP, which was one long equation, with respect to each of the unknowns. So the gradient of the IP is shown here, and the first element in this gradient, in this long vector, is the partial of the IP with respect to A1. The second, the partial with respect to A2, all the way down here to the partial of the IP with respect to AN-1. So this is a gradient which contains equations, and there are as many equations as there are unknowns. There are 5n plus 2 unknowns, so this is a vector of length 5n plus 2. In order to determine the slope of the gradient of the IP, the Jacobian of the IP has to be calculated. The Jacobian of the IP is shown here. It is comprised of a number of different sections. In the upper left-hand section, shown here, these terms are associated with the dynamics of the system, and they are a function of the matrix R, where the matrix R is given below. The rows and columns which are in the green section are associated with the boundary conditions. They are a function of the matrix G, where the matrix G is given here. And lastly, in the red section, those rows and columns are associated with the implementation of the interior point method, and they are a function of the matrix K, which is given below. The gradient of the IP can be driven to zero using a Newton-Raphson method, where Newton's steps are calculated by taking the inverse of the Jacobian and multiplying by the gradient of the IP evaluated at the present state. This gives us a vector, delta x, which contains the change in the state such that these changes point in a direction that is away from the zero location of the gradient of the IP. Therefore, it's easy to update our states such that we're moving in a direction which is toward the zero of the gradient of the IP. We take the present state and we simply subtract from it a constant, which is a Newton parameter between 0 and 1, times a change in the parameter, which was obtained from delta x. How do we solve the total problem? We start off by initializing the unknowns, and there are limitations to this initiation due to the interior point method. We then initialize these parameters alpha and mu, where mu is a parameter used in the interior point method. We then iterate until the norm of the gradient of the IP is small. We can then change alpha and mu, iterate again, and when we come to the point when the change in the states and the change in the control is small, we call that the final solution. Here is a comparison of results for 3 different problems. For the problem of L is equal to 0.3, for the problem of L is equal to 0.2, and for the problem of L is equal to 0.1. For the situation where L is greater than 2.5, the results are always the same. What's shown in the y-axis is x. X goes from 0 to 2.5 and then back down to 0. For the situation where L is between 1/6 and 1/4, the situations are similar. X starts off at 0, it goes up to L, meets L at 1 point, and then returns to 0. For the situation where L is less than 1/6, these solutions start at 0, go up to L, they remain at L over a period of time, and then they go back to 0. What's shown in this figure are the numerical results from this discussion, as well as the results which came from the calculus of variation solution of Bryson and Ho. The two are the same. Here are the control results for these 3 different problems. For the situation where L is equal to 0.3, and for that matter, for any L greater than 0.25, the control response is always a constant at -2. For the situation where L is between 1/6 and 1/4, the response, the control input starts at a low value, rises linearly to a point, and then falls back to that same value. For the situation where L is less than 1/6, the control input starts at an even lower value, rises to 0, remains at 0 over a period of time, and then falls back down to its original value.